I was asked why it's true that a path integral on the negative half space projects onto the vacuum. So if you have any quantum system with ground state omega, and let's assume that omega has zero energy, then the projection on the vacuum is the limit as t goes to infinity of e to the minus th. Because as t goes to infinity, all states of positive energy will be killed, and the ground state is left invariant. So e to the minus th is computed by a path integral with imaginary time t. I'm drawing it as if it's quantum mechanics, so I'm not giving any spatial directions. Quantum mechanics, you only have time. It lives at a point. In field theory, we do a path integral on a slab of width t to construct e to the minus th. But then if you want to get the projector onto the ground state, you have to take t to go to infinity. So in the limit that t goes to infinity, we just get a path integral on the lower half plane. So a projector onto the ground state will turn any state into a multiple of the ground state. But we wanted to know that the multiple was 1 in the case of a path integral in the lower half plane. So to compute the norm of the state that generates, we take its inner product with itself. So if this is psi, then the inner product of psi with itself, well, we need another path integral on a half plane to construct one constructs the bra and one constructs the ket. Then we glue them together, which means we identify the two boundaries of the two half planes. And that just gave us a path integral on the whole plane. The whole path integral on the whole plane gives us the exponential of minus the volume times the energy density. And usually we renormalize the theory so that the energy density of the vacuum is 0. So then that's 1. Now, this is a special case of an extremely important construction, which I think I probably used again yesterday afternoon, and we certainly will use several times later. If you have any manifold S, then there's a Hilbert space of states on S. And a lot of times, you want to construct a nice state in this Hilbert space. A standard way to do that is to pick a manifold W whose boundary is S. Then we let, let's say, phi W be a field on W. Phi S is a field on S. Well, okay. What are we trying to do? We're trying to make a state in H sub S, but as you probably know from your studies of field theory, more explicitly, a state in H sub S is a function psi of fields on S. So we're trying to construct a nice function of fields on S. And a standard way to do it in this setup is to define that psi of phi S is a path integral over all fields on W with the boundary condition that phi W restricted to S is phi S times e to the minus action. In other words, we do a path integral on W as a function of the fields on S. And that gives us a function of the fields on S, which is a state. So what we did here was a special case of that, where S was, let's say, R3 if we're in 4 dimensions, and W was a half space in R4, the lower half space. A lot of times, in many applications, S and W will be compact. In this example, they were not. Anyway, both for my lectures and lots of other things, it's helpful to be familiar with those things. So today we're going to start with the Euclidean approach to black hole thermodynamics. which actually corresponds to section 6 in my lecture notes. So this started with the work of Gibbons and Hawking, not too much after Hawking's discovery of black body radiation from a black hole. So they started with the Schwarzschild metric, and they noticed that if they just continue to Euclidean signature by letting t be minus it sub e, where t sub e will be my name for Euclidean time, they got a metric which is still real, but now of Euclidean signature. All that happens is that the coefficient of the first term becomes positive. Well, first of all, we might ask, why did rotating to Euclidean signature give us a real metric? Well, the basic reason is that we had a symmetry. The Lorentz signature had a symmetry, t to minus t. Now, the metric was real in Lorentz signature. The Lorentz metric was real for real t. So therefore, if we analytically continue it in t, that means that Gij of t bar is Gij of t bar. That's a function that's real for real t. But if I take t to be imaginary, let t be minus ite, this relation would tell us that Gij of minus te is Gij of te bar, which does not tell us that it's real. So generically replacing t by te would not give us a real metric. However, the reason it works in this case is that we have a symmetry, Gij of t equals Gij of minus t. And therefore, combining that with this relation, well, you see, t to minus t is the same as te to minus te. So this relation here becomes Gij of te equals Gij of te bar. So that explains why the metric remains real after the simple continuation from real to imaginary time. It happened because there was a symmetry under changing the sign of the time. And something similar is true in the reverse direction and will be important later. If you start in Euclidean signature with a symmetry, such as E2 symmetry under which TE is odd, will enable you to continue to a Lorentz signature metric when TE is imaginary. Now, okay, so first of all, the Euclidean, so that metric is, I'll call it the Euclidean Schwarzschild metric, or just ES for short. So the ES metric is first of all real and positive. In other words, Euclidean signature. But the main observation about it, which was made by Gibbons and Hawking, and is quite remarkable, is that if we interpret TE as an angular variable, then this metric is smooth and complete. It's a completely non-singular good metric if TE is an angular variable of the correct period. Now, to see that, we could first So to see that, we need to zoom in the region near r equals 2 gm, where the metric is obviously nice, except at r equals 2 gm, but at r equals 2 gm, the coordinates we're using are actually not good, as you'll see in a moment. And it's not obvious that this is a good metric at r equals 2 gm, because one coefficient blows up and one goes to 0. So to investigate the claim that it's a nice metric, we have to find better coordinates at r equals 2 gm. So as a first step, we define a useful coordinate near r equals 2 gm, which is this one. And then you find the metric we find this form for the metric. Now let's look at the behavior near r equals 2 gm. The reason I made this change of variables is that it puts the metric in a form where it's very easy to take the limit r goes to 2 gm. Here we just replace r squared by 2 gm squared. And here we replace r over 2 gm by 1. So near r equals 2 gm, ds squared is just r tilde squared dte squared over 4 gm squared plus dr tilde squared plus a constant times d omega squared. So it just factors as a product of two two-dimensional metrics. This one is a sphere of radius 2 gm, but it's decoupled from the rest. And this is what we have to look at. And if you look at it, it might remind you of the metric of a plane in polar coordinates. So a metric you would all know is dr tilde squared plus r tilde squared d phi squared is r2 in polar coordinates. If phi is an angular variable of period 2 pi. So, given that we know that, you see, this metric is the same if we give TE the correct period. If TE is an angular variable with period 8 pi gm, then this first bit just becomes the metric of the plane in polar coordinates. If we assume any other period, then we get a metric. You see, this metric is flat regardless of the assumed period of phi. But if phi has a period different from 2 pi, we'll get a flat, it's flat away from r equals 0, but it will have a conical singularity at r equals 0 generically. So this metric generically will look like so. It's the metric on a cone, where the cone angle is the period of phi. If that period happens to be 2 pi, then we get a flat metric on the plane. If some other period, there's a conical singularity. One way to make one of the wrong period is to start with the plane, and then this point will be the origin. Then we cut out a portion. So what we're left with is some angle theta. And then if we glue together the top and bottom, we'll get a cone, which can be nicely embedded in R3. You're all familiar with such cones. It's intrinsically a flat two-manifold, except it has a curvature at this point. So in general, we're going to get a conical singularity, which will be the delta function in the curvature. And that does not obey Einstein's equations. So Einstein's equations are obeyed at r equals 2 gm, which is the same as r tilde equals 0, if and only if the period is 8 pi gm. Well, we've seen 8 pi gm before. That's the periodicity in imaginary time that we keep running into when we study the Hawking radiation. The Hawking radiation was discovered basically because the correlators measured by the distant observer in the far future were periodic in imaginary time with a period of 8 pi gm. The explanation of this given by Gibbons and Hawking was roughly that the Schwarzschild solution itself is periodic in imaginary time with that period. Now, let's look at this metric near infinity. Well, okay, so near infinity means as r goes to infinity. So we just have, so the coefficient of dt e squared goes to 1, and the coefficient of dr squared goes to 1 near r to infinity. So near infinity, we just have, well, this part here becomes dr squared. This part there becomes the metric of R3 in spherical polar coordinates. And this part just becomes the metric of a circle. The circle has period beta, where beta is 8 pi gm. Hawking's beta. So the geometry is just a circle times R3, and something that you probably either know or if you're near the beginning of your studies of quantum field theory will soon learn is that in quantum field theory, a path integral in R3 times a circle is a way to describe a thermal ensemble of fields in R3 at inverse temperature beta. The basic reason is that the circle corresponds to computing trace e to the minus beta h. If you want to compute trace e to the minus beta h for fields in R3, you'll do a path integral on S1 beta times R3. A path integral on S1 beta times anything, where S1 beta is a circle of circumference beta, will give you a thermal ensemble on anything. That's just a general statement about quantum systems, quantum statistical mechanics. So near infinity, so if we expand around this classical solution, let's discuss the path integral on the Euclidean Schwarzschild solution. So first of all, there's going to be a classical answer, which is the exponential of minus a classical action. I'll call it the Euclidean Schwarzschild classical action. Then there's going to be a one-loop effect, which will give 1 over, if there are only boson fields, it will give 1 over the square root of a determinant. Then there will be higher order corrections. So, well, first of all, this is a Euclidean metric that describes a black hole near the origin, but it just will describe a thermal gas near infinity because of the period beta. So the idea of Gibbons and Hawking is that this factor will contain the black hole thermodynamics, the classical black hole thermodynamics. Now, the one-loop correction will contain near infinity a free thermal gas of gravitons and other particles, if there are more fields in the theory. If it's pure gravity, it'll just be a thermal gas of gravitons. The higher order terms will give interactions and the interactions include an instability. So, as we discussed, the thermal gas in infinite volume is really unstable, and we'll discover that if we try to calculate the two-loop contribution. So, this path integral for this system is supposed to describe the black hole interacting with in equilibrium with the thermal gas to the extent that that makes sense in an asymptotically flat space-time. In particular, the classical action is supposed to contain the classical black hole thermodynamics. So what I've described here is the partition function of the system. Yes? Well, it depends on the theory, but assuming we're doing pure Einstein gravity, it'll be the determinant of the one-loop fluctuation for the gravitons. And of course, that needs to be gauge fixed, so there will be ghost determinants as well. It'll be the determinant of whatever operator the particular theory has. Any other questions? So
Hi.
to...
Sorry, I have a question.
Yes, go ahead.
Does the near infinity contribution to the determinant dominate, or is it just is this just a statement about the near infinity limit?
Well, near infinity dominates because most of space is near infinity, far from the black hole. So if you ask it, what is the free energy of this system? The free energy, well, we haven't yet calculated it, but the philosophy is that the free energy has a term of order 1 over g, which is going to be the classical term. And then there's going to be sort of the volume of space, which is really infinite, but with an order 1 coefficient. That's the free energy of the infinite thermal gas. If we want to make, as always in statistical mechanics, if we want to get a finite answer for the free energy, we need to cut off the thermal gas. What's finite is the free energy per unit volume. And then there's a correction that's both order 1 in the volume and also order 1 in 1 over g, or order 1 in g, which is the interaction of the thermal gas with the black hole. Roughly speaking, once you know that this path integral produces both the black hole and the thermal gas, it has to somehow describe their interactions. So it's obvious that there's going to be a classical piece. Well, we haven't shown that the classical piece is A over 4G, but it is obvious that to do this path integral, we have to compute the classical action of the solution. I will show you that gives A over 4G. It's also obvious that we're going to get the near infinity, the free energy of the thermal gas. Once you know those two, it's also clear that whatever is the quantum interaction of the black hole with the thermal gas will have to occur as part of this one-loop determinant. And then, of course, there also are, in principle, are higher-order corrections. If we really want the higher-order corrections to be well-defined, we should work with a negative cosmological constant, which we'll discuss later. Any other questions?
When we are, if I understood correctly, when we are doing this expansion with the path integral, we are just doing like a perturbative expansion.
Yes.
Are there like non-perturbative effect which comes in, or?
Well, no doubt. The question is, well, as always in physics, perturbation theory only gives you an approximation. Here we're trying to get the semi-classical picture right. And the whole point of the lectures is to explain to you that in the semi-classical limit, you discover that black holes have a side that you didn't suspect classically. They're thermodynamic beings. So we're not aspiring to get exact answers, which normally is out of reach in physics. We're only aiming to convince ourselves from many different points of view, and I'm only going to be able to explain a small part this week, that black holes have this thermodynamic interpretation. Any other questions? Okay, so to recover the Bekenstein-Hawking formula, well, roughly speaking, all we need to do is to compute the classical action. What did I call it? I called it, I think, I sub s, the action of the Euclidean Schwarzschild solution. Well, let's explain that a little bit better. In thermodynamics, the partition function is usually interpreted as e to the s minus beta times e. In other words, for any quantum system, e to the s is the number of states, and each state contributes with the factor e to the minus beta e. So the partition function of a thermal system is interpreted as e to the s minus beta e, which is often also called e to the minus beta f, where f is the free energy. So therefore, s minus beta e is log z. And if you use the first law, dE equals T ds, you discover a well-known formula where I always have trouble remembering the sign, which you find that S is 1 minus beta d by d beta of log z. So if you take this relation, but you also know this one, then differentiating, you'll discover this formula for S in terms of log z. And in the classical limit, in other words, we're going to try to calculate S to order 1 over g. That's what I mean by the classical limit. For the leading term, z is approximately the exponential of minus the action. So S is then 1 minus beta d by d beta log z, but log z is minus the action. So now that justifies the statement that all we have to do to calculate the action is to compute the entropy, is to calculate the classical action. However, computing the classical action is trickier than it sounds. The Einstein-Hilbert action is minus 1 over 16 pi g times the integral of the scalar curvature. But the scalar curvature is 0 in any classical solution. So how can we possibly get anything interesting for the action of this classical solution or any other classical solution of Einstein's theory? Well, the answer to that question is really that the Einstein-Hilbert action is adequate for deriving Einstein's equations from a variational principle. But as input in a path integral, the usual Einstein-Hilbert action isn't quite adequate. The reason is it involves second derivatives of the metric tensor. So in ordinary quantum mechanics, if you want to calculate quantum transition amplitudes, it's not a good idea to use an action that has second derivatives of the metric. So let's discuss, first of all, something that works and then something that doesn't work. Why isn't this working? I must have disabled the thing that okay, now I have a new page. It's all right. So for a free particle, well, here's a good action for a free particle. Now I'm going to write down a bad action from which you can derive the same Euler-Lagrange equation, but you'll have trouble if you try to use it quantum mechanically. So I1 is the good action. I2 will be the bad action. If you try, you'll discover that from I2 you can get the same Euler-Lagrange equation as from I1. Well, why do we use I1 and not I2 when we're quantizing? Usually in quantum mechanics, you want to do something like calculating the amplitude that a particle starts at x1 at time t1 and ends at x2 at time t2. Well, okay, sorry. Better just to say we want to calculate the matrix element of e to the minus IHT between x1 and t and x2. That's a typical thing which we would calculate in quantum mechanics. I've put an I in the exponent, so this will be a real-time path integral, but I could have used an imaginary time path integral. So we'll do that by integrating over all paths with the boundary condition that, let's say, x of 0 is x1 and x of t is x2. So Feynman taught us to do this. Well, you could ask why we don't do the same thing with I2 instead. It won't work well. The first thing that will happen to you is that Feynman will tell you to look for a critical point of the action. So that means you want a stationary point of the action for a particle that starts at x1 and ends at x2. Trying to do that with I2, well, with I1, first of all, it works. With I1, you learn that the variation of I1, assuming the boundary conditions, x of 0 is t1, is x1, x of t is x2, and the action is an integral from 0 to t. The variation of I1 is the integral of the variation of x times x double dot. So a critical point of I1 that obeys the boundary condition is just a solution of the expected classical equation of motion. The variation of I2 instead is what you want, plus some unwanted boundary terms. There are more terms. Another term you get is delta x dot times x evaluated between the endpoints. That extra term makes it impossible to find a critical point of I2. So I2 is going to be a bad action to use in the path integral. And that's because it had second derivatives of x. Well, in the case of the particle, the textbooks use I1, and they don't really usually tell you why not to use I2. And it seems like a silly thing to do to use I2. Because in the case of the particle, by integrating by parts and throwing away a surface term, we can reduce I2 to I1. So there wasn't any reason to do this in the first place. Einstein's theory is the rare theory where you can't integrate by parts to get rid of the second derivatives in the action. So for GR, there's no integration by parts to remove the second derivatives of G. So you can't just integrate by parts to improve the Einstein-Hilbert action, but there is a surface term you can add. You can fix the problem by adding a surface term. And the surface term is the Gibbons-Hawking-York surface term. Y is York, and Gibbons and Hawking I've already mentioned. And, well, you can read precisely what it is in textbooks in general relativity or even in my lecture notes. But since I'm not going to be able to explain everything in these lectures, I'm going to proceed avoiding telling you the details of the Gibbons-Hawking-York boundary term. I'll just tell you that there is an improved action that we should use, plus a boundary term. And we should use that term in computing the action, in evaluating the entropy from that formula. And if you do, by an elementary, although slightly tricky calculation explained by Gibbons and Hawking and also in section 6 point something of my lecture notes, you'll find that you get A over 4G at the end. So that's a very important calculation that you should all make sure you're familiar with. But there's something like 20 years later, in 1993, okay, it's a very beautiful calculation and it gives the answer A over 4G, but it's not obvious why A over 4G is going to come out. It's obviously at something, but it's not obvious that it's going to be the area over 4 times. It's not obvious the area of the horizon is going to come out. In 1993, and then with improvements by other people, the first paper I know is by Karlip and Teitelbaum. I'm not absolutely sure it's the first. Found a way to do this calculation with less detail and obviously giving the answer A over 4G. And I decided that I had to prioritize what I was going to actually explain, and I decided I would explain this calculation and not the original one of Gibbons and Hawking. Once again, for anyone who wants to learn the subject seriously, you should be familiar with both calculations, and you can indeed find them both in my lecture notes. So, what are we going to do? We're only going to need to know 2 things. Well, see, remember, what was good about I1 and not I2 is that when you vary I1, there was no boundary term in the equation of motion. And when you vary I2 instead, there was an unwanted boundary term in the variation. Something I should explain is that the Euclidean Schwarzschild solution doesn't have a boundary in the usual sense, but it's not compact. And you do have to consider a sort of large radius limit of the Gibbons-Hawking-York boundary term. In other words, you could cut the spacetime off at a large radius r, it would have a boundary, and then you would have the Gibbons-Hawking-York boundary term. You take r goes to infinity, and the boundary term doesn't approach 0, so it has a limit that you have to keep. It's slightly trickier than I'm explaining, but basically the idea is that there is a large radius limit of the Gibbons-Hawking-York boundary term, and you need to include it in computing the action. In fact, the whole answer comes from, in one approach, the whole answer comes from the boundary term. See, in one approach, since r is 0, there's no bulk contribution to the action, and the whole answer comes from the boundary term. That's the original approach of Gibbons and Hawking, and as I've said, you can find it in all kinds of places, including my lecture notes. That's one approach to calculating the action, but there's another approach, which I will explain instead, where the whole answer comes from the horizon. So the action will be the same, but there are 2 strategies to calculate it. With one strategy, you only get a term at infinity. With the other strategy, you only get a term at the horizon. Roughly, the 2 calculations differ by an integration by parts. So we only need to know 2 things about the Gibbons-Hawking-York surface term. One is that with it included, there's no boundary term in the variation of the action. So the variation is given by the naive formula. Whatever it is. Plus no boundary term. We needed the Gibbons-Hawking-York boundary term to make that true, because if you just vary the naive Einstein-Hilbert action, there would be a boundary term in the action, in the variation. The role in life of the Gibbons-Hawking-York boundary term is to make this statement that I've written true, that although the action is defined with a boundary term, its variation has no boundary term. So this is the statement that I prime EH is like I1 of the free particle, while the naive IEH is like I2, the bad one. So I prime is the improved Einstein-Hilbert action for which the naive statement is true. There's another fact which I think we're going to need, but it's slipping my mind quite when we'll use it, which is just that the Gibbons-Hawke-York boundary term is the integral over the boundary of space on a manifold M. In general, it is a boundary term, so on a manifold M with boundary partial M, it's an integral over partial M with the induced metric, which I usually call H, of something local. We don't even need to know what the local thing is, we just need to know that it's the integral of something local. I think we're going to use that in a little bit. Yeah, we will. So we need to know these two facts. So we need to know that the Gibbons-Hawke-York boundary term, first of all, fixed the problem so that the naive variation is true with no boundary term in the variation. And two, although we don't need to know exactly what the Gibbons-Hawke-York boundary term is, we need to know that it's the integral of something that can be defined locally. The local thing is, in fact, up to a constant, the trace of what's called the second fundamental form, or extrinsic curvature, times something like 1 over 8 pi g. Okay. Exactly what it is, though, we won't need to know. We only need to know these two facts. Now, we want to compute the entropy, which is minus 1 minus beta d by d beta of the action. So it won't do to know the action just at one value of beta. We need to know how the action changes if we change beta, since we need to know the derivative with respect to beta. But we only need to know how the action changes in first order when we change beta. And we're going to exploit that in a clever way, which, as I said, was, I think, first by Carlip and Teitelbaum. Okay, we'll compute it in a second. But one thing I want to point out, I can't remember if I said this yesterday or not, but it is important, so I do want to point it out. The action is definitely of order 1 over g. So the answer we get is going to be 1 over g times something. And that tells us that if the entropy is some function of a over g, it will be linear times a constant. So remember, in the very first lecture on Tuesday night, I said that Bekenstein had the Hawking area theorem, which told us the area always increased. So he guessed that the black hole entropy was a multiple of the area. But a question nobody asked me was, well, area squared is also always increasing if area does. So why didn't he think that the entropy might be a multiple of the area squared? Well, you could read Bekenstein's paper and see what you think of why he said it should be just the area. There's Wheeler's heuristic picture that it's the area because there are local degrees of freedom on the horizon. That's a good reason possibly to suspect that the correct function would be the area, not the area squared. But here we see it must be the area because it's going to come from the classical action, and the classical action is proportional to 1 over g, not 1 over g squared. So even without computation, we learn that if the entropy is a function of the area, it's linear in the area. Okay, how are we going to do this computation? Well, we have to calculate the derivative of the action with respect to beta. So that means we'll take the Euclidean Schwarzschild metric and change it a little bit when beta changes. And then we'll calculate the derivative, and that will give us the action after a little while. But how do we change beta? Well, one thing which we can do, and this is the original procedure of Gibbons and Hawking, is vary m in the classical solution so beta changes. And the equations of motion are still satisfied. that's actually the procedure where the whole answer comes from the Gibbons-Hawking-York surface term. What Karlip and Teutelboim and a lot of other people have done is to vary beta with fixed m. M is the mass. So m is a parameter in the metric. I've written the metric, I keep writing it. Where is it? Come on, where is it when we need it? Gosh, it's amazing how hard it can be defined when you want it. The metric is written in terms of m, not beta. But for each m, there's a beta that makes the metric smooth. If we want to change beta, we could change m in such a way that the new beta is the correct beta for the new m. And that's what Gibbons and Hawking used. So their point of view was that they had a family of classical solutions labeled by m, or equivalently by beta, with beta being 8 pi gm. So they had a family of classical solutions that depended on beta, and they computed the action for each beta, and then they differentiated to get the entropy. And if you do that, everything comes from the surface term in the action. That's kind of obvious because the bulk term vanishes. But there's a procedure which in a way is simpler and has the benefit of explaining what the area of the horizon has to do with it. So Karlip and Teutelboim said, no, keep m fixed. So use exactly the same metric without changing the formula. So the metric will still be 1 minus 2 gm over r dt e squared plus all the other stuff. But you change beta. You regard TE as periodic with period beta, where beta isn't necessarily equal to 8 pi gm. And that means for generic beta, there is a singularity at the horizon. Now, why can we use the second procedure? Well, so let delta beta g be the variation in 1, where we change beta but also change the parameter m in the solution so that the equations are still a beta and the metric is still smooth. By the way, if the metric isn't still smooth, the equations aren't a beta. They're violated at the horizon by conical singularity. So when I said we change them both so that the metric equations are beta and the metric is still smooth, that was redundant. I could merely say that we change beta and we change m so the equations are still obeyed. That forces us to keep the metric smooth. And let delta prime beta of g be any other variation with the same change in beta. And beta is a parameter in the metric at infinity, right? Beta is this, sorry, let me tell you to interpret that beta that way. So in other words, at infinity, we have R3 times S1 beta. So let delta prime beta be any change in the metric, which at infinity looks like a change in this parameter beta in the metric at infinity. But we do anything we want in the interior. These are first order changes in the metric, right? So I claim that the variation of the improved action is the same for delta beta g or delta prime beta g. Why is that true? Well, it's true because delta beta g minus delta beta prime g is a variation of the metric with no change at infinity. By definition, delta beta and delta prime beta are two different ways to change the metric, where you change beta at infinity in the same way, but you do something different in the interior. So since they are the same at infinity, only different in the interior, the difference is a change in the metric with no change in the asymptotic behavior. But as I told you here, property number 1 of the improved Einstein-Hilbert action is that under any variation with no change at infinity, the change in the action is a multiple of the equations of motion in first order. And since the starting point is a solution of the classical equations, that means that there's no change in the action if we change the metric by delta beta minus delta beta prime. So therefore, instead of the Gibbons and Hawking procedure of changing beta while changing the metric in such a way that the classical equations of motion are still satisfied, we can possibly do something simpler by changing beta and doing whatever we want in the interior. So the procedure of Carlip and Teitelboim was just to change the period of TE with no change in the formula. Well, no change in M. In other words, the metric is given by exactly the same formula. And the only difference is that TE has a period that's going to be beta, not necessarily 8 pi GM. Now, these procedures will only give the same change in the metric to first order, because this nice formula that we're using is for first order variations of the metric. But since we're trying to only to evaluate the entropy, we only need to know what happens if we change the metric, change beta in first order. So therefore, this procedure is good enough for computing the entropy. So what's going to happen to us? Well, let's compute 1 minus beta d beta of the action with this procedure. So one term to worry about is the boundary term at infinity. But I told you the boundary term at infinity is a local integral. And the boundary is just something times the circle of circumference beta. So IGHY is going to be beta times something. And 1 minus beta d by d beta annihilates beta. So the boundary term doesn't contribute to the action. Now we could worry about the bulk Einstein-Hilbert action. Away from the horizon. Well, it's 0 because the scalar curvature is 0. But suppose we were doing something more complicated like Einstein-Maxwell. Then the bulk action would not be 0. But it would be a local integral. So it would be proportional to beta when we change beta. So, well, the Einstein-Hilbert action is 0, but if we were doing Einstein-Hilbert-Maxwell or Einstein-Hilbert something else, if we were doing any generalization of this problem, or if we had negative cosmological constant, for instance, there are all kinds of things that could make the bulk action not be 0. Although literally, for Einstein theory, in 0 cosmological constant, it's 0. But if the bulk action isn't 0, then just because it's a local action, local integral, it would be beta times something, where something is independent of beta. And that would again be 0. So no matter what the theory is, neither the boundary term at infinity nor the bulk action is going to contribute to the entropy. So the entropy will have to come entirely from the horizon. Well, why are we going to get anything from the horizon? We'll get something from the horizon because when we vary beta, we've created a conical singularity. And the conical singularity will mean a delta function in the scalar curvature. And the delta function in the scalar curvature will contribute to the action. So the action will receive a delta function at the horizon, and that's the only contribution it gets, because all other contributions are proportional to beta and are killed by the 1 minus beta d by d beta. So now we just need to investigate conical singularities. Suppose we have a metric on a plane with the wrong period for theta. Maybe I should better say that theta is equivalent to theta plus 2 pi plus epsilon. If epsilon is 0, that's the plane in polar coordinates, but otherwise there's a delta function in the scalar curvature. So the scalar curvature is minus 2 epsilon times the delta function at the point P. P is the apex of the cone. When I need to work out the coefficient in this formula, I usually use the Gauss-Bonnet theorem. I'll just do it quickly for you. An example of something that you might know from the Gauss-Bonnet theorem is that on a two-sphere, for any metric on the two-sphere, the integral of the square root of curvature of the scalar curvature is 8 pi. That's the Gauss-Bonnet theorem. Now, an example of a metric on the two-sphere is to take two identical squares and glue them together. That gives a metric that's flat except for 4 conical singularities. Each with theta plus pi. So epsilon is minus pi. So to satisfy this formula, such a singularity has scalar curvature 2 pi times the delta function. And so that checks this formula when epsilon is minus pi. So the formula in general, there's a version of the Gauss-Bonnet theorem from which you could deduce this in general, but usually I remember it except for the coefficient, and what I've just told you is how I always remind myself of the coefficient. So before I finish this calculation of the entropy, any questions on what we're doing? Okay. All right, well, okay. So now, we're interested in the case where 2 pi plus epsilon is beta over 4 gm. In other words, if beta is 8 pi gm, that's the smooth case where epsilon is 0. But for general beta, we have a conical singularity with that value of epsilon. So the scalar curvature, therefore, now it has a delta function on the horizon. In 2 dimensions, the apex of the cone was just a point. But here, we have a cone in the directions normal to the horizon, but the singularity is supported on the whole horizon. So we have a delta function on the horizon, but by the symbol delta h, I mean a delta function that integrates to 1 over the directions normal to the horizon. And the coefficient of the delta function is minus 2 epsilon, where we should get epsilon from this formula. So the scalar curvature is minus beta minus 8 pi gm over 2 gm times the delta function at the horizon. And this will contribute to the Einstein-Hilbert action. And so it contributes minus 1 over 16 pi g integral d4x square root of g times r. So we integrate over the directions normal to the horizon, picking up the delta function with this coefficient, and then we integrate over the horizon. So the integral over the horizon gives us a factor of the area, and the integral over the normal directions gives us this factor minus beta minus 8 pi gm over 2 gm. And there's a minus 1 over 16 pi g already sitting there. So finally, the action of, this is the action, complete action of the, up to a constant times beta, you see. There were some terms proportional to beta that we didn't contribute because we knew they couldn't contribute to the entropy because they were proportional to beta. Now we computed the contribution of the horizon to the entropy, to the action. We again got a term proportional to beta, which again won't contribute. So the only term we actually care about is this term. So you see, in that term, the m's cancel and some g's cancel. So we get a over 4g minus a over 4g. There are three minus signs here, here, and here. So we get minus a over 4g plus beta times something. And we don't care about the coefficient of beta because it won't contribute to the entropy. So finally, the entropy is 1 minus beta d by d beta of the improved action of, sorry, there's a minus sign here, of a over 4g minus beta times something. This doesn't contribute. And 1 minus beta d by d beta acting on a over 4g just gives a over 4g. So we get a over 4g for the entropy. So this calculation had two virtues. One is that it shows that the answer comes from, in some sense, from the horizon. But the second is it's very general. So this calculation was sufficiently general that it applies equally to Einstein theory, Einstein-Maxwell theory, Einstein-Maxwell theory with a cosmological constant. Well, the question is there a physical intuition for this result? Well, is there a physical intuition? Well, there isn't a better physical intuition for why the entropy is the horizon area than Wheeler's suggestion that it comes from local degrees of freedom near the horizon. If that's true, you would like to have in the classical physics a calculation that makes it manifest that the answer is the horizon area. You see, otherwise, for each theory, so Gibbons and Hawking originally did a mildly tricky calculation with the Gibbons-Hawking-York surface term. You can read it, as I've said, in my lecture notes. And in my lecture notes, I'll also explain later on, I think with a cosmological constant, this similar calculation. So you can do what look like slightly tricky calculations in each case, and they all look different. It seems like a miracle that you always get the area. This calculation is supposed to help you get intuition. Well, part of the intuition you're supposed to get from this is that it's useful to think in terms of a metric that would have had a conical singularity at the origin. That has a lot of applications, some of which are in my notes and fewer of which will be in my actual lectures, because I'm starting to see I'm running out of time. This calculation is supposed to help us get intuition.
Sorry, I have one question.
Let me finish
Yeah.
my sentence. This calculation is supposed to help us get to intuition by manifestly giving the area as the answer. So that's supposed to convince us that this is probably a good way to do the calculation, as opposed to other ways which are very ingenious, but where it looks like a miracle in each case that you always get the area. This has the beautiful property that for all kinds of theories, this discussion is valid, and it automatically gives the area. Yes, there was another question.
Yeah, I wanted to ask what happened with the entropy from outside that was added to the generalized entropy to fulfill the second.
Well, the question is about the following. So the generalized entropy is A over 4G plus S out. And here we only discussed the classical piece, not S out. That's true. The justification is that the classical piece is 1 over G, and this piece is of order G to the 0. So when I said the partition function was the exponential of minus the action times a one-loop correction, S out will show up in these corrections because it doesn't involve a 1 over G.
Maybe related to this, there was one question on Zoom, whether you can say a few more words about its determinant calculation and why it gives the thermal gas.
Well, the fact that the determinant gives a thermal gas at infinity is something that one will learn when one studies quantum statistical mechanics, even at the beginning practically. the determinant gives the partition function, and the partition function of what? So the path integral of anything on a circle of radius beta gives the partition function. If the anything you're studying is a free field, the partition function is a determinant. So the determinant is the partition function. The partition function describes a free gas if what you're studying is a free field theory. So zeroth order in G. Okay. When one studies quantum statistical mechanics, or at least statistical mechanics of quantum field theory, more or less the first thing one will learn is that black body radiation is described by the determinant of a free field. I'm afraid I'm straining to think of a better way to say that. I suspect some of you here who have taught quantum statistical mechanics more recently than I have will have better explanations in mind, but unfortunately I'm the one answering the question.
Can I ask one more question?
Yes, please.
So we use the conical singularity in the metric as a
Yes.
tool,
Yes.
but is there a physical picture associated with metrics with conical singularity?
Well,
What kind of system that would correspond to?
I can't give a better answer than to say that using this trick with the conical singularity has proved to be a very efficient way to understand entropies. And in a way you should, well, I wish I could say that you should ask again after my lectures are finished Friday, but I can see I'm not going to be able to explain everything I wanted to. So I might end up referring you to the lecture notes to see more examples. But I'm pretty confident that if you go more deeply into the subject, you'd be convinced that this is a useful way to look at things. For example, considering a conical singularity is a good way to analyze S out to further respond to some of the previous questions.
So in Wheeler's picture, where we subdivide the area of the black hole in little G spots and then count the qubits of it that you mentioned in the lecture, of course, I know why you're looking at it from the G perspective, but G doesn't have the units of area, right? So if we reintroduce the speed of light and the other constants, we get something like the area over 4 Planck length squared. And then you could interpret sort of that each Planck length squared has about a qubit. But
Well,
then the factor of 4 is very weird there. Do you have any intuition where
Well,
the factor of 4?
no, I actually want to reject the question because Newton's constant traditionally was normalized in a certain way. You might ask Newton whether he chose the right definition of G. Any other questions? Okay, we're going to go on then. So, I'm going to say something again, which I think I have said before, but it's such an important point I want to repeat it. We computed the entropy, but is it a counting of states? The answer to that question is presumably yes, because black hole thermodynamics works. But it's definitely not obvious why. And that you could consider that as the one way of stating the deepest mystery in the subject. It's not obvious why, because the Euclidean Schwarzschild has the wrong topology. For the thermal gas, well, suppose we had a thermal gas with no black hole. We would use a topology R3 times S1 beta, and then, well, I was asked why the path integral in R3 times S1 beta gave the partition function of a thermal gas. Well, the person who asked about why the determinant is related to the thermal gas might not have realized that was the question that was being asked, but it was, because the determinant is the partition function for the free field. So, you see, the partition function on R3 times S1 beta is obviously a trace because you can formulate it in terms of initial data on R3, then you propagate for an imaginary time beta, and then you glue the top to the bottom, and you've constructed a trace. So to say it another way, you get a trace because the states are running around a circle. And in quantum field theory, normally when you get a trace, the reason is there's a circle, and the states are running around the circle. Now, the topology of the Euclidean Schwarzschild is wrong. I always wish I had the metric handy when I need it, but the important thing is that R never goes to 0. R is bounded below by 2gm, right? When we decided it was a smooth geometry, we discussed the behavior at R equals 2gm, but we never let R become less than 2gm. So R is at least 2gm throughout this spacetime. That means we wouldn't change the topology if here, just replace R squared d omega squared by 2gm squared times d omega squared, or any other constant times d omega squared. That wouldn't change the topology. So the topology, and here we've discovered topologically this was the plane in polar coordinates, right? So the topology of the Euclidean Schwarzschild is R2 times S2. For the thermal gas, the topology is R3 times a circle. So for the thermal gas, you do have an interpretation as a sum over states. An interpretation of the path integral as a sum over states, because there's a circle and the states are running around the circle. For the Euclidean black hole, there's no circle. So the experience is, and believe me, this week I'm only going to be able to scrape the surface in conveying this to you, but the experience is that black hole thermodynamics works, but it's not clear why it works, because it's never clear that the things you're computing really come from sums over states. In this approach, with the Euclidean path integral, it's not clear because the topology is wrong. There's a circle at infinity, but there's no circle in the interior. So remember, near infinity, this looked like R3 times S1 beta. But that's completely wrong in the interior. The way it's wrong, you could think of R3 near infinity as being sort of half line times S2 times S1 beta. These are the angular directions. This is the radius that's going off to infinity. Let's put some lower cutoff. And that's parameterized by, S1 beta is parameterized by T sub B. So near infinity, the Euclidean Schwarzschild and also the thermal analog both look like R plus times S2 times S1 beta. The question is, what happens when R becomes smaller? The R plus is only valid when the radius is sufficiently big. In the thermal gas, well, first of all, R goes all the way down to 0 and the S2 collapses to a point. In the Euclidean Schwarzschild, the S2 never collapses, but the S1 beta shrinks to a point at the horizon, because that's what happens in polar coordinates. The S1 is the circle of polar coordinates, which shrinks to a point at the origin of polar coordinates. So the topologies are different as to which of these two factors is shrinking away in the interior. And it's because the topologies are different that it's a total mystery why the Euclidean Schwarzschild calculation is computing a sum over states. You can think of that as a statement of the main mystery of the subject, although this main mystery has got zillions of manifestations. So on a different day, I might have told you something else was the main mystery. But anyway, this is one statement of the main mystery. Are there any more questions?
Since you mentioned that this analysis holds for Einstein-Maxwell theory as well, I was wondering what it would imply for an extremal black hole, for instance.
Actually, this analysis applies for an almost extremal black hole, no matter how close it is to being extremal. But in this derivation, I think you have to think of the extremal black hole as a limit, because the topology changes in the extremal limit.
Let me just ask an additional question. You're asking about whether S counts something, but it
Yes.
counts something. We don't know what the states are, which
Yes.
it count. So I mean, that
Yes.
you could say is the reason why we don't know what it counts. But you say on top of this,
Well,
there's a second.
no, sorry. If there was a circle here, we would have found the states that this counts. If we had a circle times something, the states would be the states on the something. So,
We don't have a quantum gravity. This is what's confusing me.
well, formally, we don't have an exact theory, but we don't also have any, but see, usually in physics we don't understand things exactly, but we've got some idea. So, if the topology was S1 times something, I still wouldn't be able to describe exactly the states on the something, but we wouldn't have the same mystery. The states would be the states on the something of whatever the theory was, and if we only knew the theory approximately, we would only describe those states approximately. But here, since the topology is wrong, with this topology, even if we did know the theory, we still wouldn't be able to interpret this calculation in terms of accounting of states. Any other questions?
Should we look at the holographic principle as a solution to this problem? So
The what principle?
the holographic principle. We always think about the holographic dual of the gravity theory,
Well,
and there we are able to count the states.
Well, most people don't regard that as an answer, but rather an argument that the question does have an answer. In other words, I think I don't have anything useful to tell you.
Okay.
Most people regard duality with the conventional quantum theory as something that gives you encouragement that what you're looking for exists. But most people think they want to understand quantum gravity and understand why these understand in some way from a bulk point of view why these computations are describing thermodynamics and entropies.
Can I ask about this?
Yes.
Does this mean that we shouldn't do a calculation in Euclidean and we should do it in Minkowski or what?
Well, I started in Lorentz signature on Tuesday night. I suspect that many people are familiar with this Euclidean calculation and possibly not with Hawking's original calculation or the slight refinement of it I explained. Because I think the Euclidean calculation, in a sense, is more straightforward to explain. But the physical principles are extremely unclear because there's no circle. The reason I started in Lorentz signature, and the reason I think it's important to start in Lorentz signature, is that although the Lorentz signature calculation is also mysterious and doesn't explain what the quantum states are, at least the physical principles in computing emission from the black hole were completely clear. So I think one of the main reasons to believe that the Euclidean calculation is correct is that it gives results that agree with the Lorentz signature calculation. So to reiterate, well, okay, the experience is definitely that the Euclidean calculations work and are very powerful. But it's also true that why they work is not at all understood and is lacking a better explanation. It's because of that that, to me, it's important to start in Lorentz signature where the physical principles are clear even though the answer is mysterious. Yes?
Are there other terms that we can introduce besides Hawking-Gibbons that could arise in this specific example? Or so
Well-
is this case unique in that?
Well, if you want the bulk action to be precisely this one, then there's a unique Gibbons-Hawking term that you can add on the boundary to have the two properties I stated. The two properties are a good variational principle, and the boundary term is local. And those are the only properties we needed to compute the entropy, and it's also, we don't need to, for this calculation, we didn't need to know it was unique, but in fact it is unique under those conditions. But what you should have asked me is if the bulk theory is unique. Clearly not, because we could add all kinds of things to the bulk theory. And depending on what we add to the bulk theory, we may also need a boundary term. But, well, first of all, if there's no boundary term that agrees with the two properties, that tells you that this bulk action was bad. But if there is a boundary term that agrees with the two properties, then you can do the calculation I've just explained. But the answer will come from the horizon. But it won't be simply the area. The area is what you get from this bulk action. But other terms in the action will give other contributions at the horizon. Of course, at long distances, that is for a big black hole, the Einstein-Hilbert action by far is expected to dominate over higher dimension terms in the action. Any other questions? Okay. If not, I guess we should go on just for a little bit. So what I'd go on to next is to, well, I had two minds about whether to discuss the case of negative cosmological constant or to skip it. The argument for skipping it was primarily that the ideas are the same as what I've told you for lambda equals 0, so it seemed like something we could skip. The main argument against skipping it is that I really wanted to explain eventually the Ryutake-Nagi formula, and that's hard to explain unless we're familiar with lambda negative. A counter-argument to the last argument is that I might run out of time for Ryutake-Nagi anyway. So I was at a slight quandary for what to do. But I think we should spend at least a little bit of time to discuss negative cosmological constant. I've been told that it's better if you don't go to lunch till 1. And in that case, in that case, I can go on a little bit past 12:30, I guess. So, first of all, anti-de Sitter space, or ADS, is the maximally symmetric space with negative cosmological constant. So it's the analog of Minkowski space. And it has a metric that can be written in many ways, but here's one way. Where V is 1 plus R squared over B squared, and B is related to the cosmological constant, which is here assumed negative. So minus 3 over lambda is positive, so B is real. So that's the Lorentz signature version. And again, we can let T be minus ITE, and then we get a Euclidean signature version. And here, you see that V is positive everywhere because of the 1. And since V is everywhere positive, this metric is smooth with any period of B, of TE. We can assume any period beta for TE. And that will be a smooth metric in Euclidean signature. And it will, so topologically, it'll be R3 times S1, where the R3 is described, doesn't have the standard flat metric. the metric is 1 over v times dr squared plus r squared d omega squared. But because v is 1 near r equals 0, as we see here, this is a smooth metric on R3. Near r equals 0, it looks like the standard flat metric in spherical polar coordinates. So beta is a sort of temperature parameter. But beta is not the inverse temperature that you would measure if you lived in the space. If you live in the space-time, well, if you live here, you see we have dTe squared times v, which is 1 plus r squared over b squared, dTe squared. So the circumference of the circle at let's say r equals r naught is r naught over b times beta. That means if you live in this space-time, you would sort of see beta going to infinity at large distances, which means the temperature goes to 0. So whatever energy you have, it's too much if you're near infinity, because any particle is much hotter, has much more energy than the temperature if beta is going to infinity. So that's a heuristic explanation. That any particle that goes off to infinity is reflected back. You can make math, and those of you who have studied the ADS-CFT correspondence, as suggested by one of the previous questioners, would be familiar with it. You can make math to show this, but heuristically, any particle is reflected back from infinity because the effective temperature is going to 0 there. Another way to say it is that the proper energy of the particle goes to infinity there because of the behavior of G00. So since beta is a sort of temperature parameter, we can describe a sort of thermal gas in anti-de Sitter space with any beta. But as I've just told you, beta is not really what you'd interpret as temperature if you live in the space. The modern interpretation is that beta actually is the temperature in the dual conformal field theory that lives on the boundary of space-time. I'll say a few words about that in a bit. So one thing we can do if we want to study a thermal gas in ADS is this is a perfectly good solution for any beta. Or we can look at the black hole in ADS. So the ADS Schwarzschild solution is given by the same thing, but now V is different. Exactly the same formula, but with a different V, describes a black hole. So everything else is the same. I'll write it in Euclidean signature, but it's in either Euclidean or Lorentz signature. The same thing describes a black hole, but with a different function V. But the topology is different because V is no longer positive definite. You see that V becomes negative if R is sufficiently small. So we let R plus be the largest zero of V. And so M is the ADM mass of the spacetime. Well, you could call it the mass of the black hole. With R plus being the largest zero, you can solve for M in terms of R plus, and you'll find that M is R plus over 2G times 1 plus R plus squared over B squared. So that formula shows you that as R plus increases from 0 to infinity, all values of M occur precisely once. And that monotonicity is related to the fact, as we'll have in a second, that the thermodynamics can be stable. Well, it will be stable if R plus is sufficiently big. So going back to this solution, you see that if m is small, well, if b is very, very big compared to m, the fact that the cosmological constant is negative gives us this term. But if m is small, then you basically have a small black hole in a large anti-de Sitter space. So you have a small black hole that in a space-time that's cut off at infinity by that fact that it becomes very cold at infinity in the way I explained. On the other hand, if m is sufficiently large, the black hole can't be approximated at all by a asymptotically flat black hole, because if m is too large, this term becomes important before this one does. So when this term becomes important at smaller r than this one, we have approximately a flat space black hole embedded in anti-de Sitter space. In the other region, we have a very big black hole in an asymptotically anti-de Sitter space-time, but it's completely different from a flat space black hole, asymptotically flat space. Now, there's no close analog of Hawking emission, because a Hawking particle going off to infinity would be reflected back. Because as I explained to you, everything gets reflected back, because it's so cold out there, as seen by an observer living in the space-time. But there is thermodynamics. So there's no problem with the Euclidean derivation of the black hole thermodynamics. So for the Euclidean derivation of black hole thermo, well, you see, V is going to 0 at r plus. And therefore, we're in the same situation we had before. Before, we had 1 minus 2gm over r times dt e squared. And that was going to 0 at r equals 2gm, which forced us to eventually interpret Te as a periodic variable and to compare it to polar coordinates. We have the same general idea. V is still going to 0 at r plus. So similarly, the right change of variables will show that r equals r plus is like the origin of polar coordinates, and Te has to have the correct period to make the metric smooth. So if you do that exercise, you'll find that the black hole is smooth if Te has period beta, where beta is 4 pi r plus times b over b squared plus 3 r plus squared. So the computation, getting this formula, I think, well, you could work through it with my lecture notes or with the original Hawking Page paper. I forgot to say that. What I'm explaining is due to Hawking and Page around 1982. But the important qualitative property is that as r plus goes from 0 to infinity, well, beta is 0 when r plus is 0 and also 0 at infinity. So there's a maximum value of beta. So if beta is too big, there's no black hole. That means if 1 over beta is too small, there's no black hole. If beta is small enough, there are 2 black hole solutions for the same beta. So since that's the case, well, with 2 solutions, you'd want to know probably which one has smaller free energy. But what actually happens here is that one of the 2 solutions is thermodynamically unstable and the other is thermodynamically stable. You can guess which one should be unstable as follows. If r plus is very little, we basically have a flat space black hole that happens to be embedded in anti-de Sitter space. But we know that the asymptotically flat black hole is unstable. Remember, it had negative specific heat. So that suggests that this small r plus solution is unstable, and the large r plus solution is stable. Stable means positive specific heat. Unstable means negative specific heat. So from formulas I've written, you can compute this specific heat and verify that for sufficiently small R plus, it's unstable. For sufficiently big R plus, it's stable. Now, as I've said, the modern interpretation is that the parameter T is the temperature in a dual conformal field theory on the boundary. Hawking and Page 40 years ago didn't have that interpretation, but their point of view was that you specify the boundary condition. They did the same calculations we do in ADS CFT nowadays. They just didn't exactly have the same words to go with it. They specify the metric near infinity, and they asked, how can they fill it in with the least possible action? And they assumed that would dominate. So we have two fillings. Well, okay. We have some solutions as a function of beta. If beta is big, what we might call ADS beta, which remember was R3 times, topologically R3 times beta, S1 beta. Remember, we have the solution that exists for all beta. So there's the solution with no black hole that exists for all beta. And if beta is big, that's the only solution we have, so we expect it dominates the path integral. If beta is small, we have ADS beta, but we also have the black hole solution, in fact, two of them, small r plus or large r plus, but one of them is unstable. If beta is small, there are two locally stable solutions. Locally stable means they're stable against small fluctuations. To know which one is truly stable, you'd want to minimize the action. So, in a certain range of beta, where there are two locally stable solutions, you have to calculate the action of the two solutions and see which one has lower action. Well, how do you calculate the action? Well, the action here is the Einstein-Hilbert action with the cosmological constant. I always have trouble remembering. I think it's just r plus 2 lambda, but can't promise the plus 2. Then there's the Gibbons-Hawking-York boundary term. It turns out that in asymptotically anti-de Sitter space, the Gibbons-Hawking-York boundary term doesn't contribute. So you actually now have a more naive, you have a more simple calculation conceptually, but because the cosmological constant is not 0, it's not true that the bulk action doesn't contribute, as was the case before. For negative cosmological constant, r plus 2 lambda is not 0. It's a multiple of lambda. So the action is the volume of the space-time, which is infinite. But you regularize it by subtracting something which is, well, a way to say it is that what you're really interested in is comparing the action of two solutions, the one with and without the black hole. That difference is finite. And the sign of that difference determines whether what's truly stable is the thermal gas or the thermal gas plus a black hole. So Hawking and Page found the Hawking-Page transition. Sorry, there were two locally stable solutions for beta less than some beta naught. which means for t bigger than 1 over beta naught. So there's some beta 1 less than beta naught, such that the black hole is truly stable at beta less than beta 1, and the thermal gas with no black hole is truly stable at beta bigger than beta 1. So there are two locally stable solutions, but they exchange dominance as a function of the temperature at what's called the Hawking-Page transition. So one expects, therefore, that with beta less than beta naught, so they're both locally stable, but one of them is absolutely stable, the other one should be metastable. So one expects that if you start the system in the wrong solution, it'll tunnel to the right one somehow. But to my knowledge, that tunneling process hasn't been described, and one doesn't know, have an estimate of its lifetime. I want to say a few more words about this, but I think it might be a good time to stop for questions, and I'll say a few more words after lunch.
But in real life, the cosmological constant is positive.
Yes.
So what will we learn from this? That's not so clear to me.
Well, what do we learn from ABS-CFT correspondence? You see, this
But
kind
for
of...
the
this
no,
kind
but for
kind
the
of-
prob for
this
this
kind
problem.
of... Well, black hole thermodynamics proves to be extremely robust and gives sensible answers no matter what we do. So I don't know why you didn't object when I studied the asymptotically flat case. But, yes, and you could have said the real world is a cosmology, so in asymptotically, any locally symmetric space is wrong. You could have asked me to put in everything from the real world. But the experience is that to the extent gravity makes sense, black hole thermodynamics makes sense. And so Hawking and Page were playing around with it, and they tried a negative cosmological constant. And in some respects, it was a little bit more interesting because it has this phase transition. One thing we gain is that, okay, at beta less than beta 1, the black hole is truly stable, which means we have a truly stable state of the black hole in equilibrium with radiation. So in the earlier lectures, I had to apologize that what we were studying is unstable if you go to higher orders. Here we have something which is truly stable, which is believed to be because it's dual to the boundary conformal field theory, which we believe is truly stable. But because it's truly stable, we can push our theoretical calculations much farther. And, well, we can argue that things make sense in higher orders, which we actually can't do with zero cosmological constant. So from a theoretical point of view, this is actually a very robust playground for discussing black hole thermodynamics. But have no fear, after lunch we're going to let lambda be positive. We have...
The other day you mentioned that the theory of gravity seems to know more than it should.
Yes.
I was wondering if by now we have some example of this.
Well, to me, it's a matter of taste how much you think the theory of gravity should know. So the fact that black holes obey the first and second laws of thermodynamics seems a little bit more than gravity should know. But if you want to know more beyond that, there's all kinds of more. All the things connected with the Ryu-Takanagi formula have to do with gravity knowing more than it should. I would say that the more deeply you go into the subject, the more you'll be convinced that gravity knows more than it should. Yes, I see another question in the back.
Hi, hello. So this construction seems to imply that away from 4 dimensions, in odd dimensions, there will be a logarithmic divergence in the action.
It's unfair to ask such a detailed question, which 90% of the audience has no idea what you're talking about. when
Okay,
I'm
so,
trying to give elementary
I'll ask a more
lectures.
general question. Can
Yes,
we
please.
use this construction in other dimensions?
Yes. I've set the dimension to be 4, but nothing I've said starting Tuesday night depends on 4 dimensions in an essential way.
Is there any symmetry breaking involved in this Hawkins page phase transition?
That's actually an excellent question. So is there a broken symmetry in the Hawking-Page transition? So in the work of Hawking and Page did not have an answer to that question. There's a modern interpretation of all this in the dual conformal field theory. I will say a few words about that after lunch. Not enough to explain it systematically. Some of the questioners obviously are more or less experts on it and are asking questions appropriately, but for the rest of you, I want to explain just a little bit. Well, mainly because in case by some miracle we get to the Ryu-Takanagi formula, we'll need to know it. But anyway, in the context of ADS-CFT, your question does have an answer. So in the dual conformal field theory, it depends on the details of the setup, but the dual conformal field theory can be something like a gauge theory where confinement or deconfinement are expected depending on the temperature. And then the Hawking-Page transition. Well, I think your question is really, is there an order parameter for this phase transition? In the boundary CFT, the order parameter is a thermal Wilson-Polyakov-Hooft loop. That's the quickest answer for me to give. But not everyone will understand that answer. Explaining that answer requires going into the ADS-CFT correspondence in much more detail than we will have time for.
I have another
Yes?
question. So how do we see that the metric under the interpretation that the Euclidean time is an angular variable, that the metric is complete?
Well, it was complete near the horizon because it was simply the metric of a plane in polar coordinates. That's complete. The other thing you could worry about is what happens near infinity, but the metric was already manifestly complete near infinity. It just looks like R3 times a circle. Assuming you know that the metric of R3 is complete and the metric of R3 times a circle is complete, it just looked like that near infinity.
Okay, so these properties of smoothness and completeness, one sees them because there is an isomorphism between the metric and the metric of the plane and so on.
Locally, it can be approximated by the metric on the plane. The only reason I mentioned completeness was the following. If you wanted to simply make the metrics smooth, a stupid thing to do is to throw away the horizon. Then it's smooth for any beta, but what's wrong with it is it isn't complete. The horizon is a finite distance away, so if you throw it away, you have a metric that's not complete. If you want the metric to be complete, you have to keep the horizon, but then to make it smooth, beta has to have the correct value.
Sorry if you have already mentioned this.
Yes?
In the case of non-zero cosmological constants, the integrand is not zero, so there are bulk contributions to the...
There's actually only... When you subtract... Well, in the point of view of Gibbons and Hawking, Hawking and Page, you subtract the action for the two solutions, and you find that the Gibbons-Hawking-York boundary term cancels. And so you only get about a bulk contribution in their way of doing the calculation.
Again, will this be proportional to the area?
Well, what's proportional to the area is 1 minus beta d by d beta of the action. But here we're actually interested in the action, not just the entropy. So, the entropy. Okay. There's a yes answer to your question if you ask about the entropy. So let's discuss the entropy of the two solutions. There's the thermal gas, which is R3 times S1 beta. In order 1 over G, its entropy is 0. Because a thermal gas always has an entropy of order 1. It has a lot of particles, but the multiplicity of particles isn't exponential in 1 over G. The black hole has an entropy which is A over 4G. If you want to prove that, Hawking and Page did that before this Karlop-Teutoburg calculation with the conical singularity was done. So they did it by a bulk calculation, which I think I actually wrote in my lecture notes. But the calculation based on the conical singularity is sufficiently general that it applies immediately to this case. That's for the entropy. However, you see, if you want to know which solution is more stable, you actually need to know which has lower action. So you want the action difference. So it's not sufficient to know the entropy. You actually want the difference of actions. And the difference of actions comes entirely from the difference of the bulk integrals. The Gibbons-Hawking-York terms are not zero, but they're the same for the two solutions. There's actually more about this in my lecture notes or in the Hawking-Page paper than I really want to explain. As I told you, I considered not talking about negative cosmological constant, but for the reason I said, I decided I should. In other words, either in these lectures or else in your subsequent study, you no doubt will want to know about the Ryu-Takanagi formula, and it's hard to explain it without being familiar with negative cosmological constant. Any other questions? Okay, I guess we'll call it time to quit.
Exactly, and we come back at 2 o'clock. And thank you.